Okay, so this is one of the two methods for balancing redox equations. This is using oxidation states, and this is going to seem pretty intuitive, probably, just because it is. The second method we'll get into more when we get further into electrochemistry, because we're going to talk about half reactions, balancing by the half reaction method or using electrons. But let's just stick with the easier thing for now. You'll notice that I've got the example from chapter 410, which is a copper solid plus a silver ion yields solid silver plus copper ion. If you did the making copper reaction in chemistry, you'll remember this from the pre-lab, where we take a piece of copper wire and we put it into some silver nitrate. You might note from class I had silver nitrate on my hand because I just did this reaction. And we end up with some solid silver, very shiny, pretty solid silver crystals, and copper up in the solution, which then turns blue because it's a copper chloride solution. All right, so what you're seeing here is I've assigned oxidation states, copper having 0, silver ion having +1, solid silver having 0, and copper having +2, and I'm looking at using these tie lines to show how many electrons were lost or gained. We know that in a redox, we have to have an equal number of electrons lost and gained because that's the definition of redox. It's an exchange of electrons. So here we can see that in order to balance this, I'm going to have 2 silvers here, which will make this 2 electrons. That is now balanced. You may just be asking yourself, well, why do we even have to do that? Notice that you don't have any other indicator that it's unbalanced other than the oxidation numbers. Let's do another example from the book. So we have aqueous hydrogen ion plus aqueous chloride ion plus a solid tin plus nitrate ion yielding Cl6 2- ion plus nitrogen dioxide gas, plus water. So if we assign oxidation states to this, hydrogen's easy, that's a +1, chlorine's a -1. Tin is elemental, so it's 0. And nitrate, the oxygen is always going to be a -2. There are then 6 minuses, but we need to come out to 1 negative, so the nitrogen's a +5. In tin, chlorine is a -1, so there are 6 of those. We need to come out to a -2. That makes the tin a +4. Here, the oxygen is a -2, so this is going to have to be a +4 to make a net 0. And then oxygen is a -2, so this has to be a +1, so there are 2 +1s. So we look at these oxidation states, and now we're looking for what's oxidized and what's reduced. Looking here, we can see that hydrogen, nothing changes. Chlorine, we go from -1 to a -1, nothing changes. These are your spectator ions. Tin, on the other hand, goes from a 0 to a +4, which means it has lost 4 electrons. Nitrogen goes from a +5 to a +4, which means it has gained 1 electron. So now we need to balance. And in order to do that, we're going to look and see that we need to have 4 nitrates. So this, we have to basically, I'm going to use another color, put a 4 here in order to make this 4 electrons, which means we have to put a 4 there. Now we just balance the rest of it. So we have, what we have, chlorines, we've got 6 on the right, so we need 6 on the left. Got the oxygens, we're going to need, what, a 4 here because that's 4 oxygens, so 8. And then we've got, do we need 4? Is that right? 4 NO3, so that's 12. So we got 8, 9, 10, 11, 12. Yeah, so 12 total oxygens. And then the tin seems to be balanced. And now the hydrogen, we have 8 on this side, which means we need 8 on the left. And now we've balanced that using oxidation numbers. And so that is pretty much what you need to do. If you're looking for another example, example 4.18 on page 176 of the 9th edition, and then your homework 87 and 88. We'll practice this some more, and we'll go over it in class tomorrow.